Good. I understand that I should start. So
Yes.
thank you very much for this invitation. I regret very much that I cannot be in Lisbon in person just to do this talk. So this idea of doing a two-person talk arises from the fact that when half of the audience is going to start to fall asleep, then Lorenzo will jump in and maybe wake you up. And maybe I'm optimistic thinking half of the audience, but so this is a joint work. So what we're going to talk to you about together is joint work with Stefano Borghini, and this is about static vacuum black holes and with or without a cosmological constant. So idea is I'm going to start a review and then Lorenzo will present you the boring details. So, having set up this stage, so what's this about? Well, the question is, can you exhaustively describe all time-independent black hole solutions of documentation equations with a cosmological constant, including a non-zero cosmological constant? And here we're talking about well-behaved black holes. So some black holes are not as well behaved as others. I'm not going to tell you what well-behaved means. It's a long story. It has to do with space-time geometry. You know, the Roger Penrose's Nobel Prize probably is at the heart of it is his Laurentian geometry theory, and so you need the whole thing to define a well-behaved black hole. In any case, this is time-independent, and time-independent can be either stationary or static. And static means that you are stationary and there is a time reversal isometry. So think of an object which rotates in a way continuously in time in a stationary way. Well, if you change time, it's going to start rotating in the other direction. So stationary is more general than static. Static is more restricted, and that's one way of understanding this. Well, there are these regular static black holes, and regular, I told you, I'm not going to define you what it is, but when you set your theory right, you're going to end up with a space-time. For the first time in my life, I'm using the symbol Z to denote a space-time because this is what Lorenzo is using. So Z is the space-time now. And so the space-time has a manifold Z, a symmetric G, which in fact should be a boldface here. And with enough global restriction on the behavior, you end up with a space-time which has the form times space. And so the time factor is pretty boring. Nothing happens in time. So you can write your metric in the static case in this form where there is a key role is played. Well, half of the key role is played by this function U, which is called the static keyed or the static potential. And a Riemannian metric, right? So the space-time metric boldface G, this should be boldface phi here, is the thing which is where physics lives, but there is this Riemannian manifold, which should be a G here, not gamma. So this is a G, and it satisfies an equation that the Hessian of U is U times the Ricci tensor of this metric G, the space metric, and Laplace U equals 0 when the cosmological constant vanishes. And now, so this function U shouldn't change sign. And the black hole arises as either a boundary of this manifold sigma, and this is precisely the set where U vanishes. And this corresponds to something called non-degenerate horizons. So you have a boundary at finite distance, and the event horizon is actually this boundary here. In the space-time you get out of this. But at least in the static case, you can also have a situation where U does not vanish, but you have an infinitely long cylinder and U goes to 0 there. So in space-time, it's really a horizon at finite distance, But when you reduce the whole problem to this Riemannian setting, then you get an infinitely long neck. And this is called degenerate horizons. And there are a little, quite a pain in all these uniqueness theorems. And I understand that, well, lambda is positive, we're going to ignore them. This is a slide from anticipating Lorenzo's part. So if you have a cosmological constant, this equation which we had here, u times Ricci is Hessian u and Laplace u is 0, becomes u Ricci u is Hessian u, and there is an extra term coming from the cosmological constant. Laplace u equals 0 becomes actually an eigenvalue problem for this function u, and u should vanish at the boundary. This is a bit like something called the Serines problem. So since this is, I understand some people in the audience are coming from the PDE side. The Serines problem is to solve this equation Laplace u plus a function of u equals 0. U should be positive. U is 0 on the boundary, and the length of the gradient is constant on the boundary, right? So find solutions of this over a determined problem. So you're imposing both a Dirichlet condition and a Neumann condition, and this becomes not a problem for you, but both a problem for the function u and the domain. One knows that the famous theorem is that this set of equation, well, omega has to be in Euclidean space. Omega has to be a ball, and u is the first eigenfunction here, right? So this is this has this flavor because well, obviously this is a elliptic equation for u, and u is supposed to vanish on the boundary. But if you take u vanishing on the boundary and look at the second equation, then this vanishes and this vanishing. So the Hessian of u vanishes on the boundary. So in fact, you have both a Dirichlet and Neumann problem here. And this is an elliptic system because the Ricci tensor is actually some kind of elliptic operator on the metric. So you have a second order equation for the metric here, second order operator on u here. Well, there's a mixing through second derivative, but that's still elliptic for this thing. So you think, well, maybe that's not too bad. And it wouldn't be too bad, except that this is this mixed problem where you're imposing both Dirichlet and Neumann conditions here. You can also think that if you look at this right-hand side of this equation, well, lambda vanishing means the Laplacian equals 0, you get immediately the maximum principle. If lambda is negative, you still have a good uniqueness properties here, but if lambda is positive, then this becomes like an eigenvalue problem, and is actually the dimension of your manifold here. So just on this basis, you think that positive u and lambda 0 or negative should be easier than lambda positive, and indeed it is. Good. So apology for the experts in GR, but I understand that not everyone is quite familiar with these solutions. So the standard examples. So standard examples, your metric here, G, is takes this, so this is now the space metric. Take this form. Here, this is the metric on a sphere, and the radial part is has this simple form 1 over u square, with this function being given by this formula. Lambda equals 0 would be Minkowski, well, would be just a flat metric, and depending on the sign, you get hyperbolic or spherical space form. This is the negative case is the anti-de Sitter space. The positive case is the de Sitter space. In each case, you have this sphere metric here. And you can add a mass to this, right? So the metric takes exactly the same form. The manifold is different now because it's an interval times the sphere. And this function acquires this extra piece here. And depending upon the value of lambda and m, you have various topologies. And Lorenzo will tell you a little more about it, so I'm not going to discuss this in detail. But let me just say that when lambda is 0, these degenerate black holes where you have an infinite region where U goes to 0 cannot occur. But when lambda is positive and negative, they can. And again, in this part that Lorenzo will be talking about, the degenerate cases are left over. There's something called the Birmingham-Kotler solutions. So Kotler was a colleague here in Vienna about 100 years ago. So he looked probably at dimension 3, in space dimension 3. All this generalizes, by the way, to higher dimensions. But he only looked at the case, what did he do? I think he just looked at the case where this constant k is 1. When this constant k is 1, we're back in this case here. But this constant can be 0, in which case here you take a flat torus metric, or k can be -1, in which case you take a negatively curved metric. So these are the standard examples in the field. A very nice one is something called the Horowitzmeier Soliton, which has nothing to do with black holes. So that if this is a talk with black holes, I shouldn't even mention them. But since they belong to this gallery of lambda equal of static solutions, let me shortly describe this solution. So if you for the moment ignore that I have crossed this out, then this metric here is exactly the metric, the Birmingham-Kotler metric, where kappa is equal to 0. And I've just this function u, I called it just to make sure that there is a mass parameter here. So in this form, if you ignore the fact that I have crossed this out, is just the Birmingham-Kotler metric. And the trick by Horowitzmeier is just to change this sign here, right? So here you had a minus, which has vanished. So this becomes a plus. So if I didn't do anything here, that would be a Riemannian metric, but I'm going to change this angle here, d theta square, to time, again, changing the sign in front. Now, this is a Laurentian solution of Einstein equations. Has nice properties. If m is equal to 0, then the 0 sets of are smooth, totally geodesic submanifolds, right? So when u vanishes, they turn out to be, it looks like this might be funny because you have this negative power here, but they turn out to be smooth, nice geodesics. You just need to choose your period of theta properly. Now, they're interesting because their mass can be negative, and it's proportional to the this parameter here, which is usually interpreted as the mass of this solution. In this case, it can be negative, while you have certainly heard of positive energy theorem, which guaranteed in many cases that the mass in general relativity is positive. Well, there's a conjecture that these are local minima of energy, and there are some partial results on this. And there are also uniqueness theorems, but again, very partial uniqueness theorems, which I'm not going to discuss because they're not as clean as the other theorems I'm going to mention today. So lambda equals 0. Lambda equals 0, there is this folklore knowledge that we have a complete uniqueness of solutions called no-hair theorems, which might very well be correct, but it's not proved in its completeness. And the theorem says that stationary, analytic, connected, well-behaved black holes are the Kerr black holes. And in red are these assumptions which I, as a mathematical physicist, don't like at all, because first, why should one look only at analytic solutions? There is no reason for these solutions to be analytic. And second, connectedness means that you're looking at space-time where there's only one black hole. But there are examples of solutions which are charged and which have many black holes. And there are various metrics which do have more than one component of black hole, which we suspect are singular, but we don't know this. And so there is no theorem which excludes this at this stage. Well, and carrying the exterior region is another story. I mean, what happens under the horizon is, we've not been thinking about this. Now, in the static case, things are much better behaved. And that's why I'm going to concentrate on the static case in this talk. And also, I should say that with Lambda, positive stationary case is a tabula rasa. Nobody knows what terra incognita, right? Good. So static regular black holes are Schwarzschild in the exterior region when lambda vanishes. A key element of the proof of this is the positive energy theorem in all dimensions, only proved recently. So we had this theorem was true up to dimension 7 until a few years ago, or when known to be true. And then we know now that it's true in all dimensions. Yes, in the analytic case, there are is progress by Neugebauer and Heinig, who show that you cannot have a solution where you have 2 black holes sitting in there, but if 3 is still possible, 25 is still possible. And the analyticity question does some partial results by Kleinem and Ionescu. So, well, if lambda is negative, things are a bit different. Years ago, we have proved that static global irregular vacuum black holes, there's many of them, right? So there exists an infinite dimensional family of such solutions near the Schwarzschild anti-de Sitter solutions. They are described by free data, which are conformal classes of static metrics at the conformal boundary at infinity, right? So that's the technical description. I'm going to explain to you a little bit what it means. So conformal boundary at infinity, you take your space-time metric or your space metric, rescale it by a conformal factor, and now this metric G tilde is a metric now on a compact manifold, and this compact manifold will have boundary components. Some of them will be the black hole event horizons, but there'll be some new components at which this function omega vanishes. So I'm wondering if I have I have probably the power wrong. This should be a -2. Sorry about this. This is omega -2, right? So when omega goes to 0 and G is tilde is well behaved, then you're infinitely far away. And so omega is also assumed to be have no zeros on the boundary, on this boundary at infinity. This is again a nice idea of our Nobel laureate this year, Roger Penrose. And now this metric G tilde extends smoothly to the boundary, right? So this G tilde is really a nice metric on this manifold, on compact manifold with boundary, and the fact that omega vanishes somewhere makes this boundary the infinity be at infinite distance. Good. And now technically the statement is, infinite dimensional family near Schwarzschild and de Sitter, but actually not for all mass parameters, but only except for one parameter, which corresponds to something called Hawking page phase transition. And we have extended this result recently to stationary black holes. So there is actually infinite dimensional family of well-behaved stationary black holes as well. So what's the story with this conformal infinity? I've already told you that you rescale the metric at infinity by a conformal factor. So this anti-de Sitter space-time, this is its global structure. In space, it's a 3-dimensional ball, or here it's depicted as a 2-dimensional disk. And at a finite infinity, you have a boundary, a finite distance in this conformal picture, but this boundary is really infinitely far away because of this conformal factor. Something similar for Schwarzschild anti-de Sitter metric, but more complicated, so I'm not going to discuss this. And there is a uniqueness theorem. If you assume that this boundary, that the metric of this conformal boundary, so the metric of the conformal boundary will be here, if it is exactly, if it's conformally the same metric as anti-de Sitter. So in other words, a round sphere metric in 2 dimensions. Then if you assume this, then you get that if there is no black hole, then this is anti-de Sitter solution, right? So you get a uniqueness theorem for anti-de Sitter spacetime in the spirit of uniqueness of Minkowski spacetime. But if you assume that conformally at infinity you have the same conformal structure as anti-de Sitter, then this is anti-de Sitter and without black holes. And this is a nice a string of papers, and this nice version is due to Lorenzo and to Stefano. If there's a theorem for black holes as well, so this is the previous one was for solution without black holes. So now we take a space slice of this black hole space-time. So we have a manifold, a Riemannian metric, and this static potential. And you're assuming that it's asymptotic to a Kotler solution. So again, you're freezing at the infinity. You're saying the structure at infinity should be as simple as possible. It's just conformal to a compact hyperbolic manifold in this case. Now, if you assume that the mass is negative, and if the boundary is connected, and if the genus, this boundary is the black hole, right? So, and this boundary is the boundary at infinity. So if the genus of the black hole is the same as the genus of the boundary at infinity, and you have negative mass, then you get a Kotler solution. So this is quite a decent uniqueness result. You could ask, well, what happens when the mass is positive? And there is a question mark here. And the question is, what about this genus? Well, I have a personal conjecture that there exist static solutions where this is not necessarily true. So the Kotler solutions have this property, but I have a, I think, well, I have some ideas how to prove that there are solutions which are static and don't satisfy this, but this is work in progress. Maybe I'm completely wrong. In any case, the proof of this theorem goes back to Lee and Neves in 2013, and based on some work I did with Walter Simon years ago. And there is a beautiful, simple proof by our colleague Borghini, just published recently. So let me just tell you a few words about the heart of this Lee-Neves proof for this black hole uniqueness. It involves a mass, and the mass is the integral over the conformal boundary of something called the mass aspect function. And the heart of this Lee-Neves proof is that their inequality, which has a flavor of a Penrose inequality, namely, if the supremum of if the mass aspect function is negative, right? So you're assuming that the mass aspect function is non-negative, then the supremum of this mass aspect is larger than this function determined by the geometry. This is the area of the black hole. This is the genus of the black hole. And equality holds actually for Kotler and constant mass aspect function. So Penrose inequality is a relation between the mass of a black hole and the area of its black hole. Well, this is in the spirit, except a bit more complicated than the original one. Well, one would like to know whether this is true if one only assumes that the mass is negative, or if the supremum of the mass aspect is replaced by mass. We don't know. That's an open problem worth looking at. And this is as far as I wanted to tell you about lambda positive or negative. And Lorenzo, it's your turn.
Okay, thank you very much. May I try to share the screen? Okay, let me try. Can you see my screen?
I cannot.
You cannot. Okay, yeah, let me try.
Yes, yes, now we can.
Is it working?
Well, for me, it's okay now.
Okay. Thank you to Piotr. Thank you also to the organizer. Let me sorry if I go quickly to the mathematics, and then at the end maybe we continue. So after this very nice and comprehensive introduction, let us now focus on some particular problem. The problem of classifying static metric. As Piotr said, we can concentrate on the Riemannian part. So we look at the Riemannian slice of our space-time, and the metric induced is Riemannian. Together with the metric and the manifold, we also have the lapse function or static potential U, and G, U, and M satisfy this elliptic system of elliptic system of equation called a static triple or static metric system. Okay, in general, so you have the equation, the system for involving the Ricci curvature, and then the equation involving essentially the eigenvalue equation for the static potential, and then you add to the equation, of course, boundary condition, and the natural boundary condition on the boundary of the manifold is U equal to 0, because this creates the event horizon, so the horizon of the black hole region, essentially the boundary of the black hole region, let's say, roughly speaking, and then in general, when lambda is non-positive, so negative or 0, you have to add asymptotic condition on both U and G, because you expect the model solution to be complete non-compact. Okay, so in this case, it's natural to ask for asymptotic condition on both U and G, and try to see that maybe the solution to this equation with this boundary condition are just few. So you classify. This is the case. Let me just quote, for example, maybe the most famous example is the black hole uniqueness theorem, in the case where lambda is equal to 0. This, I mean, the first result in this direction is due to Israel, and in the 60, and then there are a lot of improvement. Okay, so for example, in this case, it is natural, which is also the easiest case to think of. It is natural to impose. So in this case, U is an harmonic function. Okay, so system simplifies a little bit, and it is natural to ask for the metric G to be asymptotically flat, and also it is also natural to ask that the lapse function is going to 1 at infinity. So let us recall this in the following. This is an important feature, the fact that the harmonic function is a bounded one, and is going to take maximum at infinity. Okay. Okay. Let us also recall that this assumption of asymptotically flat, I mean, it is of course very natural, but also we will further comment on this assumption, because actually it is I mean, it assumes a lot of things, because, for example, you prescribe also the topology of infinity. You are saying that at infinity, essentially, the level set of U are becoming more and more spherical, essentially. So for example, we want to provide an analog for these results, also in the case where lambda is positive, where nothing was new, essentially. Okay, there was a lack of black hole uniqueness in the case where the cosmological constant is positive. Okay, which is kind of weird, because I mean, essentially, it is believed that the true cosmological constant of the universe is positive. So it is worth looking for static black hole uniqueness theorem in that case. As I mentioned, in the lambda equal to 0, the theorem says that if you have this system with this boundary condition, and boundary condition at infinity also, then the only solution is the rotationally symmetric one, meaning the Schwarzschild metric. Okay, here I just recall briefly, but actually Piotr already said that if you have a static triple, then you have also a vacuum solution to the Einstein field equation. But of course, if you have a lambda in your system for the static triple, then of course you solve vacuum Einstein equation with cosmological constant. Okay, and so from now on, we focus, as I said, in the case of positive cosmological constant, so positive lambda, and n equal to 3, okay? Our setting from now on is precisely this one. So the system is u reach equal Hn of u plus 3 times u times g, Laplace u equal minus 3 times u, a u equal to 0 at the boundary. In that case, actually, we don't have asymptotic condition at infinity because, as we will see in a minute, the model solution are expected to be compact with 2 boundary components, 1 or 2 boundary components. Okay. So the goal is to classify solution to the system star. So in principle, it could look simpler because you don't have the problem with infinity. On the other hand, it's somehow strange because I mean, somehow you have this boundary condition. In some sense, you can think of this problem as an overdetermined problem. But yeah, but the problem is that you don't have just u as a variable, but also g is part of the game. So it's not completely clear. I mean, there is a clear analogy, as Piotr was mentioning, but okay. So let's try to see whether there is also an analogy in the conclusion. So see if we can prove that actually there are just few solutions. So let us recall with the help of some picture, the model solution. So essentially they depend on a parameter m called mass parameter. Okay, and essentially the solution are of this kind. I mean, here the picture are one-dimensionless, so the circle must be understood as spheres. Okay, so essentially you have the black circle, which are the horizon of the black hole, so the black hole horizon. And also you have something which is peculiar of lambda, of positive lambda, which is the cosmological horizon, which is the boundary in green here. And in the rotationally symmetric case, okay, the model solution, which is the one for the model solution, actually your lapse function only depends on one, let's say, radial variable called r, small r. And okay, so essentially the two horizon, the black one, the black hole horizon, and the cosmological horizon, the green one, correspond to the two positive zero of this polynomial, essentially. So you look to um square, so it is a polynomial, 1 minus 1 square minus 2m over r. You look to the zeros of this polynomial and you get actually the value for the horizon. So essentially your manifold is just an annulus, essentially. So a big ball of radius r plus and a small ball of radius r minus. Also, the model of the manifold is very simple. The lapse function is that one, and the metric is given by this formula, as in the Piotr's slides. It looks like in the picture. So essentially, you have a big minimal surface, actually, a large minimal surface, which is unstable, the cosmological horizon. And then you have the black hole horizon, which is instead a stable minimal surface. Okay, and in the middle, another important point, actually, will be very crucial in our analysis, is the red region, which is again a sphere in the model situation, which is the set where the lapse function is achieving its maximum. Remember, this is a very important analogy with the infinity of the lambda equal to 0 case. Remember, I told you a few minutes ago that actually in the lambda equal to 0 case, okay, you assume that u is going to 1 at infinity, since u is harmonic and it goes 0 on the other boundary. It is strictly positive in between. Actually, u is is the supremum of this harmonic function. It is taken precisely at infinity. Okay, and okay, so let us continue the picture. So what happens when the mass parameter goes to 0? So you see that when m is going to 0, the black hole horizon becomes smaller and smaller, and the cosmological horizon is becoming larger and larger, and at the end, you get the de Sitter solution, which is so in which the mass is 0, because essentially the other solution, essentially the mass. I mean, also all these solutions are vacuum solutions, so you there's nothing in this space, but you can think in the de Sitter-Schwarzschild case, you can think of the mass as hidden behind the horizon. So when the horizon is becoming smaller and smaller, it eventually disappears. When m is equal to 0, actually you find the vacuum solution without mass, essentially, because okay, all the matter contents is gone away. On the other end, the other limit situation is when the size of the two horizons, the black hole and the cosmological horizon, are becoming the same. In this case, you have a solution which is geometrically it is a cylinder, and it is called the Nariai solution. So we want to classify to see to prove a uniqueness theory means that if you start with a solution to start here, then you want to conclude, then you have a rotational symmetric situation. Okay. So here is again a picture in which you see actually the profile of the function u. So you see the profile of the function u is this one. The generic situation, you have two zeros, and when m is going to 0, actually you have just the limit situation of the de Sitter. In this picture, actually, you lose information about the other degeneration when m is going is reaching the other threshold value, 1/3 square root of 3, because in that case, R minus and R plus are going to coincide. So essentially, they disappear here, but it's just an illusion because of the coordinate that you choose. Actually, there is a precise limit from the Riemannian point of view. Okay, actually, here is our first result. Okay, our first result in the direction of black hole uniqueness theorem is the following. So assume that sigma, you call sigma the set of maximum point. Okay, assume that there is a connected component. You look at the set of maximum point for the lapse function, which is okay, remember the analogy with the infinity in the lambda equal to 0 case, and you assume that you have a connected component which is CMC, constant mean curvature, totally umbilic, meaning that the second fundamental form is pure trace, and also that it is a round sphere, meaning that the induced metric is very nice, is the round metric, the standard metric on the two sphere. And then under this situation, you conclude that the manifold is rotational symmetric and isometric to the Schwarzschild de Sitter solution, or in the limit case, to the Nariai solution. Okay, and actually, in principle, okay, here I recall what the hypothesis. So in principle, you have a lot of hypotheses. CMC, totally umbilic, meaning that the tracelet second fundamental form, which I denote by Hij dot, okay, which is 0, and also the induced scalar curvature is constant, since we are on a two manifold. This means that the manifold is spherical. I mean, in principle, it seems that you're asking a lot, but actually, if you, I mean, this hypothesis is completely natural, especially if you think of the lambda equal to 0 case, when you ask that your manifold is asymptotically flat, because I mean, when your manifold is when your manifold is asymptotically flat, you're asking essentially that your manifold is something like this. Let me try to, I know I cannot draw a picture, sorry, but it's something that is more, I mean, such that the large sphere large coordinate sphere are indeed are indeed metric spheres. Okay, so also so you're asking essentially all this information, but in one single sentence. So you just say asymptotic effect, but you are actually meaning all these hypotheses, all these assumptions. So this is the precise analog of what is known in lambda equal to 0. Now, how do you prove that? I mean, just a sketch of a very quick idea of how to prove that. The idea is it's very nice because you use something that in general is not suited for studying elliptic system, namely the Cauchy-Kowalewska theorem, because in general elliptic problems are ill-posed. For the initial value problem for elliptic system is ill-posed, but actually here we don't want to prove existence of solution, but just use the uniqueness part. And you realize that you have an elliptic system, which is for which the hypersurface sigma is non-degenerate, and actually on the hypersurface sigma you are prescribing a nice initial value set, because u is equal to u max, a constant. Okay, the derivative, the normal derivative of u is 0 because you are on a maximum point. So of course the gradient of u is 0. In particular, the du in dr is 0. The induced metric, because I mean your unknown are u and g. The induced metric is the spherical metric gs2, and the normal derivative of the induced metric is the second fundamental form, which is again proportional to the round metric, because you're asking total umbilicity. Actually, this set of initial conditions are the same that are satisfied by the model solution. So by the uniqueness part of the Cauchy-Kowalewska theorem, you essentially deduce that your solution is everywhere isometric to the Schwarzschild de Sitter solution. So you prescribe something on the set of maximum point, and then you conclude. And now, in the remaining part of the talk, I will try to see whether see whether it is possible to obtain to prove this assumption, essentially. Of course, if you're not assuming anything else, it's very difficult. But actually, I will try to convince you that we find some natural condition under which you do actually prove that among the maximum point of u, there is a connected component which is actually CMC, total umbilical, and round. Okay, so that's the main idea, looking at the maximum point, and then we want to discuss all these assumptions. So our first result in this direction is a quite general result about extremal level set, about the structure of extremal level set of analytic function, because I mean the solution to this system are analytic. So we have this preliminary result. So if you look to a real analytic function, in general, you have a very nice theorem by Lojaziewicz, a structure theorem, saying that the critical set can be as the structure of a stratified analytic manifold. So you have various strata, sigma 0, sigma 1, up to sigma n-1, okay, of various dimensions. So sigma I is the ith stratum. And locally, this you have essentially finite union of high-dimensional reanalytic submanifold. Okay. So a priori, the picture that you may have in mind is something like this. So you have, okay, for example, in dimension 3, you have strata ranging from dimension 0 up to dimension 2. So you have, okay, singular point, and then, for example, you have sigma 1. Here, sigma 1 is given by two pieces, is sort of the shape of an 8. And then you have the green part, which is the two-dimensional stratum, the top stratum, okay? So the one given by a piece of analytic hypersurfaces. So in general, on a critical level set, that's all you can opt for. But in the case of, if you look to extremal level set, meaning the set of maximum point or minimum point, you can improve this result. That's what we did together with Stefano and Piotr. Okay, so we prove the following regularity for the top stratum. So you take a connected component of the top stratum and you assume that the Hessian of U is nowhere vanishing on the closure of sigma, then sigma coincides with the closure of sigma. I mean, in other words, sigma is regular without boundary. It's a real analytic closed hypersurface without boundary. The idea is the fact, I mean, of course, in our case, we have this, the hypothesis is satisfied because we have the equation Laplace U equal to minus 3U. And so in our situation, the Hessian is non-vanishing, even if it is, it has a lot of zero, but actually there is this component that is non-vanishing on the place where we are interested in. And then you use the regularity of simple eigenvalues, eigenvector of real analytic matrix to deduce that actually you have a well-defined tangent space, and the top stratum is a really nice hypersurface. So essentially, the first step, okay, we remember that we want to prove a lot more. We want to prove CMC, totally umbilic, roundness, but at least we start with something which is a nice smooth manifold, and that was not that was not for free actually. So in general, you don't have the stratified picture, but you have a very nice two-dimensional top stratum. Okay, and then we want to investigate okay, phytogeometric property of sigma. As I said, what is the mean curvature? Is it constant? Is the second fundamental form pure trace? Is the induced metric the round metric? If this is the case, then we can conclude. Okay, so the idea is to exploit the geometric content of the Taylor expansion of U near sigma. So you can expand, you Taylor expand your Laplace function. And what you get is that actually you can put some coefficient in evidence. So for example, you see that in the Taylor expansion, you have the mean curvature and the traceless second fundamental form, which are showing up. So maybe if you prove properties, nice properties for U, maybe you can deduce some nice geometric properties for sigma. The idea to continue is to try to, and that's very important, is try to compare our generic solution so far to a model solution. The idea is to compare with the solution which has the same mass. Actually, as I said, the same virtual mass, because actually we discovered in doing that actually there was not a clear notion of, actually there was no an accepted notion of mass when lambda is positive. So we proposed our notion of virtual mass, at least for static solution with positive lambda. But here in this circle of idea, the important thing is that actually this notion is the one that allows you to choose a model solution to compare your given solution. Actually, I will explain maybe later how to do that. And once you have done this, once you have selected the right solution to compare your MGU, your generic solution, then you can prove a gradient estimate, which is really, really important. So it is a local gradient estimate, namely that you take a connected, you use the set of maximum point essentially to divide M3 into several pieces. So the connected component of F3 minus the maximum point, and on each of these connected components, you can define a notion of mass. So you can say, what is the mass of that connected component? So this is a number that you call M. And then you can prove that the gradient of your solution is always bounded above from the gradient of the model solution of the same virtual mass. Okay, so UM is the radial solution, the radial Laplace function of the model solution. Okay, you have this inequality always true, okay, on each connected component. Okay, actually this inequality is sharp and rigid, meaning that if you have equality, then your rotation is symmetric. So it's really an important part. And before telling you how to select a virtual mass, I eventually have to prove gradient estimate. Actually, I want to show you how to conclude, okay, how to prove a theorem. So once you have this, actually, you look to some interface. So you have already proven that. So you look to a connected component sigma of the top stratum of the maximum point. So the red one, and so you fix a normal, uninormal d by dr, and then you have two sides of your manifold. You have m plus and m minus. You look at the interface between m plus and m minus. Okay. Actually, you expand the gradient of solution divided by the gradient of the model solution. Okay, um plus or um minus, depending of whether you are on m plus or m minus. You get this. Okay, so u1 minus 4/3 times h, etc., etc. And the gradient estimate is telling you that actually h/2, meaning the mean curvature, okay, of sigma is bounded from above and from below by these two quantities, m plus to the power minus 2/3 minus 3 square root, and the other one with m minus. Sorry? Okay. Okay. And then, okay, so pretend that that m plus and m minus are the same as in the model solution. So that the two virtual masses that you have defined on the two pieces are the same. Then, of course, your pinching becomes strict. Okay, essentially, h becomes constant. So if the mass of the two region divided by sigma are the same, then sigma is CMC. Okay. And moreover, sorry, if you go farther in the expansion, so here you have big O of R squared, but you can exploit this term. You go farther, actually you see that if H is constant, so if you use 0.3, actually your expansion of the quantity grad U over grad UM is in that form. But again, using the gradient estimate, you deduce that the trace of the second fundamental form must be 0. Okay, so sigma is also totally umbilic. So essentially, the condition on the masses is already giving you a lot of geometric information. It's proving the hypothesis of our first theorem, essentially. Moreover, since when you plug this information on the Ricci nu, essentially normal, you use the equation of the static system. You see that the Ricci normal is 0, and actually you combine this with the Gauss equation, which is very standard, and together with what you prove in the previous two steps, so the fact that H is constant and the trace of second fundamental form is 0, you deduce that also R sigma is constant, but sigma is a two-dimensional sphere. And so by the uniformization theorem, so you prove all the set of hypotheses that you needed, okay, in order to use our first result. So in principle, in principle, you were asking a lot of things. So you were asking a lot of feature on the set of maxima, and then you deduce that the condition on the masses is the one that allows you to prove that these hypotheses are actually satisfied. So essentially, the theorem that we get is the following: assume you have a solution. Okay, assume that it is two-sided in the sense that the maximum point is dividing M into two pieces, essentially, an outer region and an inner region, where you may have black holes. Okay. And then, in principle, you have a situation like this. So essentially, you have something very weird with several connected components of max U. But then, if the masses of n plus and the mass of n minus are equal, then you conclude that your solution must be the model solution, so as facile de Sitter. Okay, so maybe I'm running out of time, so maybe I have still some slide about how to choose how to define a virtual mass. But okay, maybe I can stop here. Maybe you can ask me if you want to know about the virtual mass. But actually, I mean, I want just to convince you that it is an important concept, because I mean it is natural. It actually gives you a natural condition to prove all these geometric properties and eventually conclude that you have uniqueness here. So actually, okay, I think that's it.